In this video, we're going to finish page 3 of your handout package for lesson 3.3, and we're going to do it in a hands-on way. So I'd encourage you to follow along on Desmos so that you can see how a lot of these functions work as well. In page 3, we are presented with a question that says a lab tech monitors the growth of a bacterial culture by scanning it every hour and trying to figure out how many bacteria are in it as those bacteria grow over time. And you'll see that in your table at time 0, which would be the initial time, the population is unknown. Okay, and that's because you can't see it right off the swab. You have to let it grow first. So what I've done is I've inputted the table that you see on your page into Desmos as such. And when you do the same, one thing you'll notice is that you can't see your points. Here's the first one, and the rest of them are way up in here somewhere. So here's an interesting feature that you can do. You can adjust the X and Y axes using the wrench. You can decide that, along the X axis, maybe I'll go from, -1 up to maybe 10 for now, so that I incorporate all of those X points. And you could punch it in here. And in the y-axis, we could also start at, say, -1, just so that you see the origin on your display, and maybe go up to, say, 500, so that all of these would display. Here's another cool thing, though. If you look down here in this corner here, it says Zoom Fit. And if you click on that, bam, it automatically allows you to see it quite nicely. And if you don't want to see, these sections of the Cartesian coordinate too much, you can bring it down here like this as well. Okay, so that's a neat feature too. In question 1, we're asked to create the scatter plot, which we've done, and we need to classify the linear relation. So in order to classify it, we need to know its R value. So let's sub in the equation then for linear regression, which would be y1 regressed against mx1 plus b. And we can see that here's the best fit line for this data, and the R value is 0.9269, pretty close to +1. Not bad, right? It's in that range of being a strong positive correlation. So the correlation coefficient, again, off Desmos, you can just pull right off of here as having a value of 0.9269. And the line of best fit we can create because M and B are given to us. So this line of best fit has an equation of y equals 75.6429x minus 142.714. And that's easily done through Desmos. Now, in part 1C of your handout, it says, we've added the line to your scatter plot. Do you think this line is satisfactory? I mean, yes, if you only look at the R value, but here's where your professional judgment needs to come in. You can recognize that this looks an awful lot more like it has a curved relationship than it does a linear relationship. Okay, even though you've got a relatively equal number of points on both sides, 3 under the line and 2 plus a couple little guys above, right? It instead looks like it might be closer to a parabolic or exponential along those lines. So the R value is great, but even in terms of the x-intercept, if we go down here, we can't have an initial population of bacteria that's in the negatives, so that doesn't really work. And if we're to look at this in an extrapolative way, in other words, if the bacteria culture were to grow, beyond 7 hours, we'd expect it to kind of go in a straight up fashion. Well, this line seems to be going in the wrong direction. It's going up, but really away from the data. So overall, is linear going to be the best fit for this? Probably not. So in question 2, it says, let's try a couple other types of regressions instead. And it suggests trying a quadratic and cubic. So let's put in the equation for quadratic, which is y1 regressed against ax1. And if I want to square it, on the keyboard here in Desmos, there is a squared button that makes life pretty easy. So we'll do that, plus bx1 plus c. And you can see here that they show the r squared value as a capital R. In our notes in our textbook, they use a little r. It's the same thing, okay? And we've got a value here of 0.9959. That is much, much closer to 1. So that's a good thing. And you'll also notice that the data seems to fit it pretty well as well. Now this is not actually a data point, this is just the y-intercept. Our data points actually started down here at a value of 1 hour and a population of 10. So just be cautious, that's not a data point, okay? And it curves along here, and these are much, much closer, okay? So in question 2, it says find the r-squared value. We can do that easily. Find the equation of the curve of best fit. So again, here are your a, b, and c values. You can plug them in respectively, changes to an equal sign, and there's your equation of the curve of best fit. Now let's do the same thing for cubic as well. So y1 regressed against ax, and I like to cube it. So if I go back into the keyboard here, I've got an exponential button here I can use so that I can put in a 3. Now I forgot to put in the 1 for x, no big deal. I just used my cursor, went back, put the 1 in. There we go. Don't have to go back and retype everything. Plus bx1 squared plus cx1 plus d. And you'll see for this regression equation, the r-squared value is also very good. It's 0.9974. In fact, it's even a little closer to a value of 1 than the parabolic or than the quadratic one is. But still, very good values for both of them. And when you view both of the curves on the screen, you can see that in the range of our data set from here to here, they're almost on top of each other. Okay, but if we go outside of the data set, extrapolating out here, or even in this direction, you notice that they're very different. Okay. So the next one says after we've graphed them, record their r-squared values and their curves. We can do that, or the equations of their curves, easily done, using the values that are displayed in Desmos. But then part D is where the nuts and bolts comes in. It says use these equations to estimate the initial population. Okay, so if I zoom into the graph here where time equals 0, I can see that if I click here on that point, it'll pop up saying the initial population of the bacteria, according to this model, suggests that there were 66 bacteria in the culture when I started, and that they actually had to dip down after an hour and after 2 hours before they rose again. And you might go, I'm not so sure bacteria would do that unless my culture was really had poor conditions for growing them. Most bacteria cultures are not of that nature. When you do them in class, you prepare sterile agar, you make sure that the only thing that can get into that, that plate is the bacteria itself. Not reasonable. This one's a little better, and this is our cubic relation. You can see it highlighted when I clicked on it there, and you can tell also by the difference in the colors of the curves too. Okay, if I get rid of this one here, let's go here. You can see the initial population of the bacteria was 25. Now after an hour it said it's 10. Again, there's a drop here, and in real life scenarios that's probably not very realistic. Okay, so both of these, while having fantastic r-squared values, when you extrapolate to initial population, don't quite fit as ideally as we think they probably should. In terms of the rest of the curve, they're pretty good, and even beyond when it goes into growth beyond, one grows a little faster than the other, but they're heading in the right direction. So question 3 says, let's try an exponential regression for this one. So let's add in the exponential regression equation of y1 regressed against ab to the exponent x. So again, I'm going to utilize this function here so I can customize it to have an exponent of x1. All right, I'm going to just take these ones off for a second just by clicking on their color, and it doesn't eliminate them, it just hides them for a moment so we can focus in on this new one. And in fact, let's take the linear one out of there too, because we know that linear is the least likely so far of all of these for a whole host of reasons. Now, when we look at this, this fits better in that it has the better general shape, okay? Its r-squared value is not so great compared to the other two. I mean, it's still very good, don't get me wrong, it's close to 1. But look what happens if we introduce this into log mode. Wow, all of a sudden, this curve fits these data points a lot better. It's starting to deviate a little bit as time goes on, but in terms of the initial conditions of this bacterial culture, it's much better. So we can get its equation by subbing in the A value into here and the B value into here, no problem. We can get the R squared value easily right here as 0.995, best R squared value we've had so far. And then in part C it says use this model to estimate the initial population. So let's go back here now and see what happens. Well, here it says, the initial population is about 5.7. Now we know it's not possible to have 5.7 bacteria as initial population, or is it? Maybe there's a bacteria cell that's 7/10 of the way of splitting, okay? This makes a lot more sense in terms of how exponential growth works for populations. And so far, this is our best model. Okay, it's good within the data. So far it's the best. It's good outside of the data as well. Now in question 4, it says, what happens if we add a little bit more information to our culture? Let's go on beyond 7 hours. So let's add 8, 9, 10, 11, 12, 13, and 14. Okay, I'll just go up here and change this. Here we go. A little too fast there. And let's add in their respective populations that are given in your note as well. Here we go. Okay. It says now discuss the effectiveness of this exponential model for adding in a little more data. So you'll remember that the exponential model was the one we did here at the very bottom, and let's zoom back out and see how it fits. There's some interesting stuff going on here, right? It's got a little bit of a boom. Okay, and the model was really, really good at the beginning, especially with the initials, but as time goes on, that exponential model doesn't seem to be the best fit anymore. And now that we've added in that data, let's take a look at the R squared value. It has dropped dramatically too. It was 0.995 before, now it's 0.8833. Now again, if you wanted to find the equation for this new curve, you could put in the new A value and B value that have come out as a result of adding more data points. Easily done. So now let's go back and see if any of these other curves are better, okay? Because there our squared values will have changed too, having added those new data points. So I'm going to take that one off. Let's go back to the cubic one. Now this is where I mentioned in the previous video, cubic is great, but here it says it's going to reach a maximum and plummet back down again. And I mean, the conditions of bacterial growth are good. We know the growth is going to continue on. So cubic again works well within the data, not so great at the beginning, but it certainly does not work well extrapolatively beyond 14 hours of bacterial growth. So let's go back to this one. Notice that the quadratic one, the shape is best. It's not perfect at the beginning. It has a negative population, but overall, if we're looking at extrapolating over time, it's got the best fit so far. And we could come up with the equation for that new model easily. The A, B, and C values have changed. Let's do a quick comparison of R values and R squared values. Again, the linear now with our new data is down at 0.9868, but we already ruled out that it really doesn't make sense, even the R value is okay. R squared here, 0.9888, cubic 0.9947, and exponential 0.8838. So we kind of narrow it down to these two being the best. So I'm going to take that one off. And take that one off and let those put those two up together. There they are. So again, when you're looking within the data, they're both pretty good. But if you want to extrapolate beyond the data, the quadratic model is going to be better than the cubic model. So Moral of the story is don't rely entirely just on R and R squared values to decide which model is best. Look constructively within the data, outside the data, and at the R value together to determine the best model.